Okay, she's recording. Okay, we've got it. Okay,
Professor,
let's
I have a
begin.
question.
Well,
Syllabus, it doesn't state that you have office hours. So if we
yes.
have questions on the homework, how do we contact you?
Okay, office hours. Let me just go just a second. I need to get a full screen here. Here we go. Office hours. Some students already took advantage of that. My office hours officially are Tuesday from 10 to 11, because 11 I have another class, or by appointment. And usually, so far, we kept the 10, 11 Tuesday, and the students send me an email, and I send them an invite, a Zoom invite, and then reach out, and that's how it works. Okay, so there's no problem. And if you have any questions, say on homework or something which is really bothering you, you can ask during class. Because assuming that it is a problem for everyone. If it's just something local, then you can do that. But if say something is completely unclear, just let me know. And maybe I went too fast or something. Okay?
Okay, sounds good.
Sounds good. Okay, so we start. All right. PowerPoint. Go here. So this is a brief summary of what we did last time. Hydrostatic, we finished. And we did buoyancy, which is very similar to what you had in high school. I mentioned that Archimedes figured that one out 2,000 years ago. So nothing dramatic. Then I had a quick discussion about stability. I think it's more important than meets the eye. But in case of a floating object, the interesting part is like I'm showing it down here. Where's my cursor? Right here. Is that once, say, the boat tilts, then actually the center of pressure moves to the right of the flotation center because of the area is changing. So even though it appears like it's unstable because the center of gravity is above the center of flotation, it still is stable. And that's why all those ships are working. The typical terminology is you decide about, say, a moment direction, and then for a force, for an angle direction. So let's say this was theta, this was phi, I called it phi. This is phi, and this is the moment. So if you increase phi and the moment keeps on increasing, that's unstable. But if increasing phi, the moment is the opposite direction, like it is described here, then it is called stable. And it's of course logical. I showed that to you with the towing that wheel, or like the supermarket cart wheel. Okay, so that was kind of a side remark. And now we're moving back to the one-dimensional flow. And the first thing we did is we introduced Bernoulli. Everybody's using Bernoulli, everybody's quoting him, and many are using it wrongly. Okay, so I tried to develop it more carefully. And let's go to the next slide. So first of all, we assumed that it is true, for example, on a streamline. But the main thing is that we try to say that there is no friction losses. So if there are no losses, okay, and the flow is incompressible, which is true for water, for air. Again, I mentioned when we say compressible, we think that the compression is because of the motion inside the fluid. So if the car goes so fast that it is really compressing the air, but significantly, then you have to take that into account. Now, if you're looking at really speed, so we're talking Mach 0.8, Mach 0.7. So there are no supersonic cars so far. So we must assume that most cases we're going to face in daily life are going to be pretty much inviscid or incompressible. Now the inviscid is no friction. So we can show cases when definitely there is no friction. In that case, we have to pick up 2 points and compare these quantities, and then we can generate the relation, which is called the Bernoulli equation. So one example, of course, was when we took a point somewhere. Let me see if the pen is working. Let me get the pen. So we take a point somewhere here, let's say far away. To the car, it appears that the flow is coming at it at the speed of u infinity. And then we pick up another point, so it's going like that, and point here, and it appears that because the flow is going around, it has to be faster. So if it is faster, then probably the pressure will be lower based on those relations. Okay, so that's what's going to happen. In this case, the height is almost the same, so the GH term will not play a significant role, or basically we're going to neglect that. So this is a typical example. Now another example, so we take this, the free stream, say point A, which is exactly the same here, and then the flow goes here, there's no friction, and then it stops. So in the process, there's no friction. If you write down the equation, then point C is going to have 0 velocity, okay, and then we just move P to here, and then the pressure difference between point, we call that A, and point C, or we call that here, I call it A, but it's the same thing as infinity. The pressure difference is this one, which is half rho u squared, which is the free stream velocity. And then based on that, there is all kind of definitions. So the total pressure, when the air is being stopped, that's called total pressure. Static pressure is the pressure outside, like PA here on the side. That would be the static. And the dynamic pressure is really this quantity here, which is the difference between the two. Okay, so that's just the terminology. We will go back to the pitot tube, which works on this principle, and we'll discuss it again. So it's no drama so far. That was, okay, we just ran away. Okay. Okay, I closed it. Okay, thank you for not playing the guitar. That's fine. That's my granddaughter has a guitar like that. All right. So where are we? Trying to go down. Here we go.
Professor, actually, I have one question. So what is U infinity, though?
I'll mute you all.
It was on the previous slide.
Okay. Somehow things are not going well for me. Was that a question or just somebody playing the guitar?
I had a question. I don't know yeah. What is U infinity? Is that like a static, or
No.
what exactly type of velocity is that, or is it just velocity?
Let's talk frames of reference. So you in your car and you drive a steady speed.
Yes.
Okay? Then the air will come at you at the same speed as you're driving, and then we're going to call that U infinity.
Okay.
Or say, suppose this is in a wind tunnel, and then this thing is stationary, and then the wind is blowing at that speed, then we're going to call it the same way. And it depends on the frame of reference, but basically it's the relative speed between the object of interest and then the prevailing flow or something. Are you good?
Thank you very much. Yes.
Okay. Let me see if this is going to, okay, it works. Okay. I don't know, I had a little problem with probably the internet or something. It didn't work well. So here's a summary of the one-dimensional model. So what we have. So before we developed the continuity and the momentum equation, and then we said steady state. Okay, we decided we're not going to make it too fancy. We stay steady state, and then the continuity says, and then we took control volume like that. And we said whatever goes in comes out. That's what it is. That's the continuity, and we try to keep it one-dimensional. Okay, one-dimensional, goes in, goes out, and then the momentum. We said Well, momentum is momentum coming out, which is this, minus momentum going in. And then if there's a high pressure here, then it's also pushing to the left. And this is a high pressure here, then it's going to push to the right. So that's what this is. These terms are. I have to take them into account. If you look at the mass flow rate, which is rho UA, then here momentum goes with the square of the velocity. Therefore, you can say that the mass flow rate times the velocity. So that's very much the momentum you discussed in high school, minus momentum in, momentum out, minus one. Same with the pressure. And now we added the Bernoulli equation, which is a third equation. And in principle, okay, so here's the difference. The first two equations, the mass flow rate and momentum conservation, they are pretty powerful. And then we're looking at the control volume. If we're trying to get the Bernoulli through that control volume and say there is friction inside or there are some losses, then that equation is not going to work. However, if we're looking outside, a flow outside of that object, very much like in a smooth streamline, yes, it's going to work. Okay. And it will be. Somebody's talking there or what?
Professor.
Yeah.
Would Bernoulli's equation kind of count as a
I
momentum equation?
I cannot hear you very well. Please increase the volume. Okay, go ahead.
Can you hear me? Would Bernoulli's equation kind of count as a momentum equation in any way?
No. People call the Bernoulli sometimes energy equation. So because we took the momentum and we integrated, if you recall. So
yes.
it is a higher order equation. So could be mass, momentum, and energy. You can look at that way. However, Bernoulli went through a whole bunch of assumptions, and the main one is no friction, because we dropped the viscosity term, if you recall. And pretty soon I'll start with a whole bunch of examples, and I really hope that it will clarify it. And you can see which cases you can work with and which cases you cannot. Okay?
Okay, thank you.
You're welcome. Okay, let's go. So, okay, here we go. So first case that it's working, you can play with that. It's very similar to basic dynamics. It's a free jet. So you have a free jet and you blow on something and then you're trying to change its direction, but the change of direction is smooth. So let's say there's a ramp and then they're trying to change the direction of that smoothly. So now definitely there are going to be forces, and you can understand that there's going to be a force. So let's see how can we deal with that. So we think, okay, so the gray is the jet, and then we surround, let me just get the plane. We surround the fluid. Actually, we can surround the whole thing with a control volume. My pen is not so great. And we're trying to see the changes. And we pick up entrance one here and exit here. So now we're trying to see what are the equations. So clearly, mass flow rate, it's incompressible. And then we can claim that the mass flow rate in is equal to mass flow rate out, no doubt about it. Then we're looking at the picture, there is nothing outside, so the pressure must be the same at 0.1, at 0.2, and outside. So if the pressure is the same, and we go back to Mr. Bernoulli, he's basically telling us, and then we of course neglect the little GH increment here. So the GH, we kind of neglect because the jet has much more momentum. So we forget about that. Therefore, Bernoulli tells us that if the pressure is the same, then the velocity must be the same as well. So now we know that the velocity in and out is the same. Therefore, coming back here, also the cross-section area of the flow must be the same. Okay? So now once decided that, then we just take simply the forces. So we're gonna, The mass flow rate is not doing much. Well, it tells us that the velocity is the same, mass flow rate is the same. And we're trying to find out what are the forces. So we go back. Fx, remember x is positive like that. Okay, this is the coordinate system. It's going to be a mass flow rate going out, which is m dot u2, but you already know that u2 is the same as u1. And then cosine theta, okay? Because now the x direction is cosine theta of that one here, okay? And coming in, it's m dot u1, but u1 and u2 is the same, so we end up, that's the force to the x direction, okay? Force to the z direction, nothing goes in, there's force only going out, okay? So this is nothing going in, but going out, goes this, okay, I muted everybody. What can I say? I mean, people are coming in and creating noises. What I'll do is I'll stop occasion and ask questions, then I unmute, because it's unacceptable that people come in and start doing all kinds.
Professor, can you hear me?
Excuse me?
Can you hear me?
I muted all, and how on earth can you talk to me? That's
Yeah, I was just gonna tell you that when you mute us, it just turns everybody's mics off. Anybody can just click and do it. So if that happens again, you can just mute us all with no problem.
okay, I'll mute all. How about now? Can you respond? No.
Yeah, I can
Yes,
respond.
in
Yeah.
case we need to interject if we have a question.
Yeah, but anytime that happens, you could just mute us, and whoever's mic is on, it'll just cut them off.
Okay, all right. Okay, back in business. So I'm trying to use the momentum here. Okay, trying to use the
Professor?
momentum.
So you're basically doing the forces in the x and the forces in the z direction?
Yeah, that's a good question. So I mentioned that's a one-dimensional flow, but I can use the remember we did the mass flow rate also at chapter 2. I did one example when the flow was coming on the top, and then I did the z. So it's actually one-dimensional flow, but I can apply that to the x or to the z direction, okay? So it's a one-dimensional flow. So what I'm doing here is I'm just using the same thing to the x direction right here. This is the x direction, and then I'm doing the same trick to the z direction. So what is coming out, the flow which is coming out is this one, but I'm interested in that direction, okay? So it is going to be sine theta, okay? M dot u sine theta. Nothing goes in because the flow comes in only at the x direction. So therefore there's this zero here, so this goes away. So the Fz is this one, sine theta. Now let's see what it means. This is a positive force, and cosine theta is less than 1, so this is a negative force. So, which means that Fx is going to act this way. And Fz is going to act this way. Now, if you recall, I said that those forces are basically, we call them the shear, which is acting on the control volume. Now, in reality, this is what the force which is required to keep the structure in place. So the fluid applies the force down, but actually the force on the fluid and on the control surface is up because you want it to turn upside. And then the same way, the Fx is actually pushing backward because otherwise the whole thing was moving to the right. My explanation makes sense?
Yes.
Okay, all right. Just pay attention to that because that's what it is. Okay, so now I can make some examples on that one. Let's do an example, see if we understand one. So here are two tricks that we can pull. The first trick is that let's say here, I touched it. I'm afraid, yeah, of course it's going to move. Of course it's going to move. Pen. Okay, so here's the situation. We have a turbine wheel, and it has this thing in it. The turbine wheel is moving, and then the jet is coming at it. That's the jet. That's this one here. Okay. Now, the linear velocity of that thing is 10 meters per second, so which is 10 meters here. But the jet itself is 15 meters per second. So the relative velocity actually, if you look at the relative velocity, is actually going to be 5 meters per second. Okay? All right, so we have a diameter here, and this is 1 centimeter, or not diameter, area, 1 centimeter square. And we have the angle, which is 120. And we want to know how much is the force pushing the turbine wheel. Okay, so the force pushing the turbine wheel is, like we said before, is getting out, which is the cosine. It's cosine 120. Remember, it's going to be cosine 120. And then minus 1. So density of the water, relative velocity, which is the velocity relative to that structure. Okay. And times the area, because we don't know what is, this one is mass flow rate times velocity. So mass flow rate is rho VA. A is equal to 1 centimeter square, which is 10 minus 4 meter. Let's see how many zeros I got. 1, 2, 3, 4. Got it right. So therefore, it's minus 3.5 Newton, which means that now there is a force here acting in order to keep it in balance. But in reality, this is the force that is pushing the wheel. Okay? And then, okay, I'll do unmute for you guys if you want to, okay, Ultra. And then the Z direction doesn't matter really, but let's see what it is. We take the same formula, same everything, and then it comes out a positive force, which means now it is pushing on the wheel down, okay? But the positive means that we actually have to push here on the structure, so it will not be pushed down. Okay, so action, reaction, the same story, very simple. What is the power generated? The power generated in an inertial flame that we're looking is actually the velocity, F times velocity. What I call it some U. The velocity is basically 5. Okay, and the force is 3.70. No, the velocity, sorry, velocity is 10. So UB, the velocity here is 10, that's what it is, here it is. And then the force is 37.7, therefore 3.75, therefore the force, the work is 37 watt, or which is joule per second. Okay, very, very simple. We just use the same formula and see how it works in terms of numbers. Here's another one. We have a wedge and we're spraying on it and it splits the jet into 2 equal parts. Okay, so we can go through the same exercise and we claim that and of course we have the control volume. Let me just get the pen right. So the control volume is there. I just put the control, this is the control volume. Okay, so goes in and goes out, here it goes out. This is the angle, theta, which is 60 degrees. And we can go back to the same formula. So this is the same formula we developed before. And now let's see. So the flow comes in and it splits equally, okay? So the same argument we had before, that the pressure is the same, therefore the velocity is the same. So the velocity here is the same velocity, which is 15, as the velocity going in here. Okay, and the area here is actually the same as these two to combine, these two areas combined. So same argument. Therefore, the force to the x-axis is going to be equal, I did it twice, like 2 times the half. But actually, what is coming out is this, and they both look the same. So rho u square a and cosine -1. Here it is given that the diameter is 0.1. So therefore, pi r squared over 4, and comes out minus 883.6 newtons. It's much higher here. It's much higher, it's a much faster jet. Before the jet speed was 5, now it's 15. And remember, it's a velocity square, so that shows a big difference. Force to the z direction, one of them is going to be, nothing goes in, but coming out, and then coming out the other direction. So there is one going here, and then there's going the other way. So eventually they cancel out. So all we have is just the force, which is negative. Here's the negative force, which we have to apply on the fluid in order to keep everything stationary, or the control station. Okay, same story. Very, very simple. Okay, one more. Let's make it a little bit more complicated. You guys still with me? Anybody makes a noise?
Yeah.
Yeah.
We're still here.
Still here.
Loud and clear, Professor.
Good. Okay, so, all right, and I see attendance went up to 120, so we're in good shape. Okay, so we have the same story I had before, but let's be more specific. So we have, let's say this is an airplane engine. I hope civil engineers don't like this example, but I apologize to them. Let's do that. That's a good example that you can actually simplify things. So what we have a jet engine, and the flow comes in. It's kind of didn't come out very nice. Comes in, and then we can call this one AA, area A here. And the area at the airplane is actually larger. We call that AI. AI, and then whatever. So the same way we can come back and say the force Fx is going to be whatever goes out. This is E section minus momentum going in, and we assume the density is the same, which is incorrect for airplane, but right now let's just do that. Again, you can change that and it's going to be correct. So it's not, we're not doing anything wrong. And then the pressure at the back, and then pressure at the front. Okay, so same formula. Now we're looking at the flow going out. Oh, here I actually changed the density. Okay, here I use the density. Okay, which is more proper. So this is the flow going in, okay, at the station here, I, and this is the flow going out, and this is exactly what we have been doing so far. Now, just for a moment, we have to remember that there is actually fuel going in here. Turns out it could be 2-3%, not too much, but still, you know, we want to be correct. So we say ME is equal the flow of the incoming flow plus the fuel. So if we modify that equation, then we end up here with the total mass flow, which is a little bit larger because of the fuel, exit, the total mass flow coming in, UI, and then same thing. Now, here is a problem. We do not know what is the area here. We do know what is the area here because that's the inlet to the engine. We know what it is, but we don't know what is the pressure here. What is the pressure PI at the face? Because that must be larger than the pressure here because there is, we could apply Bernoulli, but we don't know too many, we don't know the quantities, okay? So what we can do is, this is a nice trick. We can take another control volume. So this equation, the first one, was for the control volume which is surrounding this stream tube. We can take another control volume, which is this one. And then we can write down the equation, the momentum equation for that control volume. that control volume is basically not creating any thrust, or any force. So the force is 0. So getting out, m dot A coming out, fine. We don't know UI, we don't know what is that. M dot A going in, okay, we know this, we know the U infinity is at the previous question, that's the flight speed. We don't know PI, but we know PA, we know the ambient pressure. We know that one, that's known because that's the area. And then PA minus PA, I just put down this term again, and it's PA minus PA, which is the incoming condition, so it's 0. So now if I take that equation and realign it, I end up with mass flow rate times infinity equal UI and PI. Now we just look here, oh, we are lucky. This term is that one, and this term is this one. And then actually we did not know, we don't know this one, so there's an unknown here, and we don't know that one, there's an unknown here. So, but however here, we know this, we know what's going on. So I can actually exchange those two terms with that one, and we end up with a formula which is much nicer. So what would be a thrust of a jet engine is the exiting mass flow rate times the exit speed minus the incoming flow rate, and then the pressure at the exit and minus A. Now, any aerospace students here?
Present.
Yup.
Okay, one brave guy, okay. So turns out that this equation is very friendly because UE exhaust velocity depends on the throat. So if this is a converging nozzle like the older jet engine, then you have Mach 1 here. So you already know, so automatically you know what is the speed if you know what the temperature is. Okay, MF is like 2-3%, so the error is not much. And you know how fast you're going. And the mass flow rate, you know what the area. This is usually a very small number. So you can actually come up like a 90% accuracy of the thrust, 92%, just by using those two terms. Okay, so that's just the story. All right, but this is to show that you can go to higher levels with the simple one-dimensional model. Okay, let me continue with examples. Now, I try to put examples where we use Bernoulli. So here we go. So we have a container. Let me get the pen before it jumps away from me. So we have a container. And we open a little hole here, and we are wondering one here, one, and outside as the jet leaves, 0.2. And unless there is lots of friction here, if there's not much friction, we can claim that here's a path where the fluid particles go, and they actually accelerate, and there's not much friction. If you buy that, then we can write down the Bernoulli equation for these 2 points. Okay. Now, the pressure PA is PA. Here is also the pressure PA, so we automatically lose that term. And then H is actually representing H1 minus H2, so this is H. Okay, oh, sorry, I wrote it down to H. And then at this point 1, the velocity is 0. So this term goes away. So we end up with this. So the velocity at the nozzle exit is 2gh square root. What is the force? Rho U2a rho U square. Error. Okay, here we go. Okay, and this is exactly free fall from high school. Okay? So pay attention, I made a mistake here. Okay, I forgot the square. Okay? Can I move on? Anybody?
Yes, Captain.
Okay.
Yes, Professor.
Question. What was the question?
Oh, hello. My question is if that force on the control volume is general or only for this diagram here of the streamline.
No. The control, okay, so let me go back. I kind of stopped using the whole shebang, but I can start saying that all this is in a control volume. This is a control volume. And what is happening, nothing goes in, there is only flow coming out. Therefore, I can automatically say that Fx is going to be equal to whatever comes out. Let's call it rho U2 square A2. And then I want to say minus, but there is nothing there, nothing going in. So that would be the old fashioned. Okay, so that's what it is. Now I can use Bernoulli to figure out what is the velocity, which is here. Am I answering?
I believe so, yes.
You're sure?
But yeah, so this equation though that you have here can be used for anything that, or any situations that are like that one there.
Yeah. One more time. Okay, one more time. This equation here, which I wrote down again, and it's here too, but I just missed the two. This equation is very powerful. This makes no assumption on anything, just momentum. The Bernoulli, this one assumes that there is no friction. Okay, so but what I did here is pretty accurate because there is usually not much losses here. It's not very high speed. It just goes through and that's it. So our estimate is say 95% accurate, 97. We'll have some numbers later on. Okay?
Okay, thank you.
You're welcome. Please ask questions because these are, again, fluid mechanics is a new concept and people are using Bernoulli very freely and sometimes arrive at very bad conclusions. Okay, here's another one. Okay, so you take your hands out of the car and then you feel pressure on your palm. And you think as you go faster, the pressure increases, right? Okay,
yes.
So let's see how can we quantify that. So here's a situation. The wind is blowing. And so we're trying to look at Bernoulli now. This is Bernoulli. So the particles come here. Somewhere here it's U infinity. And somewhere here the velocity is 0 because that's it. Initially it fills up, but that it stops. So if you look at the velocity versus x, probably it's high speed and then eventually slows down and gets to 0. If this is x and u. X and this would be u. Okay, so eventually it slows down to 0, and that what you have here is you have what we call the stagnation pressure. Okay, or stagnation, I call it total. So I write down the equation here for those 2 points. So let's see, infinity here, GH, but the streamlines go straight, so GH is the same. It's gone. P infinity, okay, is the pressure here over rho, and then there's a velocity. Pressure here, but there's no, it's the P total I called it, but the velocity is 0, so we lose that one. Therefore, we end up with that relation that the P total, it's going to be equal to P total over rho. Now, let's look at this problem. Okay, so so far, what I just said is that we're trying to look at the Bernoulli, which is going this streamline, no friction, and the flow stops at that point. Therefore, the pressure rise, delta P here is going to be, so delta P, which is this equation, is going to be equal to rho half. Okay? So this is, which is the dynamic pressure, what we called before. Okay? That's what we're saying. Okay, now number two. Now we're measuring delta P with rho GH or delta H. So delta P, it's the same delta P, but it is measured with a water column, rho GH or delta H, I called it here. So let's be more specific. Excuse me. Here, this is water, and therefore this is water density. This one is air, right? So this is basically delta P, and this is the rho from Bernoulli. Okay, so this is rho. So this is how we measure water, delta P, and this is the density of air, which is coming from Bernoulli, from here. Is it clear? Again?
Yeah.
Yeah, okay. Pay attention to that one because, so now here's the solution for that particular case. Okay, we have delta H 4 centimeter, we measure 4 centimeter, and how much is air density and so on. So how much is the airspeed? So 2 times rho of the water, because this is delta P. Okay, this is delta P measured with the water manometer, and this is the density of the air. It comes out 25 meters per second times 3.6.
Na idade não era nem meu, eu baixei aqui porque...
Question or local discussion? Local discussion, okay. So I multiply by 3.6, turn it into 91 kilometers per hour, 55 miles per hour, something like this. Okay? Move on. Move on. Another one. So I'm just playing with the frames of references. Before, we've been stationary and in the air, or we've been moving into the air. And now in this case, we are stationary, but the air is coming from outside. So anyway, so it's the same story. So we have a wind tunnel, and in a sense, what I'm doing here is a pitot tube. And I'll come back to the pitot tube in a minute. So we look at a streamline. I touched it again. That's it, we lost it. So pay attention to what I'm doing, okay? So this is a straight streamline which is gonna hit that tube, okay? And this is a straight streamline which is gonna go here, almost close to the bond. So there are no friction, and then the pressure here is gonna be, let's call that, what did I call it? P, I call it P. So the pressure here in the test section is the same pressure as the velocity here, which is U, which is picked up by that port. This port, the velocity is 0 because it's stationary. So, but then what we have, the velocity outside U is also 0. So this streamline, basically the speed goes up and eventually stops here. With this streamline, the velocity goes up and stays higher. Keeps on going, which is not hitting the tube. Am I confusing you guys or not yet?
Nope.
No, never confused.
Okay, I'm happy I'm not confusing. So if I'm looking here at the problem, it's the same story as before. The pressure P outside is now the total pressure because that is the high pressure outside, and now I accelerate that streamline. So this streamline has 0 velocity here, and then I accelerate it because I'm sucking in the wind. So here I'm getting U, and therefore PA minus the pressure here is equal to the velocity in that point, half rho V squared. Okay, that's the equation. I took the air density like that, and then 1/2 rho velocity square. We said what is 150 kilometers per hour? That's 95 miles per hour, pretty fast. And that's the number, Newton meter. That's the pressure difference. What is delta H? Okay, now delta H is measured with water. Again, in the old days, you measured everything with water, and because we had those tubes which were called water manometers. So the delta P, it's the same delta P here, measure it with water, but now the density of the water is 1,000 compared to 1.2 for the air. So I just take this equation, okay, this equation, and solve for H. And this is delta P, rho GH, that's this one. Take that number, divide density G, 10 centimeters. Okay, 0.16 meters, so this is 10 centimeters. And this is how you would measure the pressure. In terms of understanding what pressure, 10 meters in the pool is about 1 atmosphere. So 1 meter is 1/10 of that, and 10 centimeters is 1/10 of that one. So this is that one. So these quantities are fairly small, but then you could have a fairly good measurement of wind speed with the water manometer. That's why people use water. For atmospheric pressure changes, they used mercury. So some of those U-tubes that you still measure the air pressure, and for telling if a tornado is coming or not, telling the weather, I think it's 76 centimeter or something column of mercury. So it's the same story. Okay, I'll move on. That was the guy about the Bernoulli. So you got that one. I have a whole bunch of those where I'm trying to confuse you, and let's see if I can. So this is very similar, but I'm changing the area. So let me try to confuse you a little bit. So here's the streamline that we're looking at. There's no friction. It has 0 velocity. Inside it has high velocity, then it has 0 velocity because it stops. So if I would do this, then I would end up with the same result. Because I can stop the air here or here, it's still going to be the total pressure. Are we good?
Yep.
Yes, Professor.
Okay, I just want to make that, because I can come up with pipes in anywhere in that system, and it's still going to be here. Now, here the velocity is slower, in this point slower than here. So I can have the static measured here or here, and then you're going to have different results. So right now it's in the large diameter. So if I take the total pressure minus the static, I will have the velocity at this section. Is it clear?
Yes.
Okay. And so I'm trying to trick you and pick up the total here, but it is the same as here. Therefore, what matters is where do I pick up the static? Okay. All right. So now let's say, so what I claim is that if I do P0, which is what I measure here, this would be P0. P0 minus P1, which I measure here, is going to be equal to U1, which is the velocity here. That is this equation. So therefore, now I need to figure out what is delta P. So I just take this equation, and the velocity in section 1 is going to be 2 times delta P over density of the air. Again, I measured the pressure with a water column. And the water column happens to be 0.15 meter, about 15 centimeters, pretty high velocity, okay? So 2 times delta P, this is delta P in water, because density of water, not G, and the height, which is given here, divided density of the air, gives me 49 plus meters second. This is very high speed because you multiply it by 3.6, you get kilometers per hour. And if you divide that by 1.604, you get that with miles per hour. So it's a high speed. What is the mass flow rate? Okay, what is the mass flow rate? I can pick up again that section here. We picked up that section here. So we say density of the air, which we mentioned 1.22, velocity we calculated 4.9, and then it says D1 is 0.3 meters, so R is 0.15, pi is pi, as usual, same as high school, 4.20 to 23 kilograms per second. Okay, these are all the same using Bernoulli, but there are little tricks that I show you that we can play with you and exams and so forth. All right. Okay, I have here something to scare you a little bit. And okay, so what my intention? And I'll get back to that later on. If I want to show the Bernoulli equation properly with the heavy going mathematics and vector algebra, so don't feel bad. I'm just doing a little bit hand waving if you don't mind. So we take the Bernoulli, or not Bernoulli, Navier-Stokes equations, okay? Navier-Stokes equation. This is the Navier-Stokes equation, if you remember. Okay, and the first term was rho, was Q, actually there was dQ dt. And then the second term was this. So if this thing turns out, if this is just algebra, it looks like that. And you know, one is the rotor. You know what? Who got an A in? What is this rotor? It's I, J, K, D, dx, D, dy, and D, dz, and then U, V, W. Those that got an A in calculus know what I'm talking about. So this is the rotor. And this is just algebra and comes up with this thing. This is an algebraic relation. You can do it and it comes out exactly like that. So now I substitute that with the Navier-Stokes equation. I remove the time-dependent story. So I'm left with this, okay? And then this rotor quantity, we call it zeta, which is called vorticity. You may have heard that term. This is some magic terms that people cannot explain what it is. But if I write it that way, and I take the body force as the gradient of GH, and then I claim that somehow, mystically, if I can make this one equal 0, then I end up with gradient of this, integrate, and voila, we end up with Bernoulli equations. Now, why am I bringing this here? Why am I trying to scare you? Because this vorticity is actually 2 times rotation speed. So if I have a fluid and it's rotating like we had with the solid body rotation, then the velocity distribution is going to look like that, which is solid body rotation. Now in fluid, you cannot find that. If viscosity is 0, then you're not going to find that. So in an inviscid fluid, this cannot happen. Therefore, vorticity means viscosity. So if the flow has no viscosity or negligible viscosity, we can assume that the friction losses are negligible. Therefore, oh, this was on its own. I didn't do anything. Did it on his own. Then Okay, so let me just reinforce my story. So then if there is no friction, okay, then we can actually end up with Bernoulli. So this is a pure mathematical proof that without friction, Bernoulli works. And not only that, there is another condition. Actually, you don't have to follow a streamline if viscosity is negligible. You can apply it everywhere. Again, I'm just trying to throw in something. Hopefully some of you will remember, some of you will not, but I think I'll come back to it again. Okay, so this is the proper proof of the Bernoulli equations. Okay, let me go on. We're still in the same chapter. I just tried to scare you a little bit, that's all. Okay, so let's go on. So turns out that based on the Bernoulli equation, people developed all kinds of measuring devices. And we're going to talk about the pitot tube, Venturi tube, orifice, and other things. And then they realized that there is friction. So somehow they put some coefficient to take account for that one. Now, let's discuss the pitot tube, okay? And after Henry Pitot, who tried to measure, French guy, tried to measure the flow in the river. So here is the pitot tube. It's a tube. There are two concentrated tubes, and the outside tube is perforated. So the inner tube is actually picking up what I call the stagnation flow. Of course, the velocity stops here, so we're getting what we call the P total here. P total, doesn't look good. Total, P total, and I said it here. So that inner tube brings out the total pressure. Nothing is moving, it's just the pressure. The outer tube, the flow goes by smoothly. So if the velocity is u infinity here, assuming that the tube is not disturbing the flow, we end up here also P infinity, so the same pressure. So clearly there is a difference. So this would be higher pressure here than here because here we stop the velocity. Okay, so if I write the equation down for this tube, then at this point, P infinity and U infinity squared, that's what I measure here. While at this point, the velocity is 0, and I measure only P total. Consequently, I can develop a velocity relation based on the pressure difference picked up by that probe. Okay, so that is how the pitot tube works. Okay, so one more time, in the old days, we had two tubes here. This was going outside in one tube. And this was going outside to another tube. I don't know how to do that. And then here we had water inside. We have water inside. So now the total pressure is larger than the static pressure. So we end up something like that. And we measure delta H. Okay. So delta P is measured by delta H, like this one. Okay, so here's an example. So we're measuring the pressure with 20 centimeters here. 20 centimeters. My drawing is not so clear because I'm drawing with the mouse. It doesn't work very greatly. In the future, I asked the university to give me one of those pen designs, pen things, but I didn't get it yet. So hopefully they will follow through. Anyway, so here's the problem. We have the pitot tube. It's trying to measure airspeed. You put it on your car, for example, and it picks up the velocity, the free stream speed that you're driving at. Here, you really want to put it up forward that it's not going to be there's not going to be interference with the velocity around the car, which could be faster than the speed you're moving. So here, in this case, velocity is measured by the pressure. How much is the pressure difference? 20 centimeters of water, Newton meter. There's the Newton meter. What is the speed? We take this formula. This is the pressure as we measured it with the water column. Density of the air, which is this one. And then we end up with 57, which is 205 kilometers per hour. So this car is going pretty fast. Okay, so this is that example. We can go and make more.
Aren't pitot tubes used in airplanes a
You
lot?
have a question?
Yeah, can you hear me?
Go ahead.
Pitot tubes are regularly used in aircraft, correct?
Excuse me?
Pitot tubes are regularly used in aircraft, correct?
Pitot tube this is exactly how pitot tube works. You can have it on aircraft, you can have it on cars, you can have it anywhere in the wind tunnel. That's how people don't measure. Now, modern pitot tubes will have 2 strain gauges here. Oops. They will have some piezoelectric pressure transducers here and here. And then those transducers will measure the velocity or the pressure difference. And there's some electronic device that is going to give you the reading of what is the speed. That's how you can buy those. Okay? Yes?
Yes.
Okay, all right.
Yes.
So another flow measuring device is the orifice, okay? The orifice is used to measure flow in pipelines, like oil pipes and whatever. And it's supposed to be fairly efficient, so you're not going to lose too much. But you want to know how much is the flow in the water pipe or flow meter. And there are different flow meters, like at your house, you have a little propeller. But in big pipelines, you really don't want to lose pressure because the propeller is not so efficient. So they developed the Venturi tube, which is Mr. Venturi, Italians, I like his sounds, 1746, 1842, 54, 76 years old. So yeah, good age for fluid dynamicist. Okay, so let's see how this thing works. We're getting close to the end of the class, so let's finish that one. So the way we're doing it is we're trying to apply, did I have the pen? Yeah, I have the pen. We apply the rules to area 1 and area 2. Clearly, here we measure static pressure, and here we measure static pressure. So it is no total. We're comparing 2 statics. So we do have the full Bernoulli. We don't have the GH. So we have P1. Okay, so we have P over rho plus velocity square half equal constant. We write it down for this section, we write it down for this section, and we end up with this. This is Bernoulli, okay? Now, we can actually look at the continuity equation because the same amount of flow.
Professor,
Yes, sir, go ahead.
how do we know that that's that constant equation? Where did we get that from?
That's the Bernoulli equation.
Okay. Oh, okay. I see. Oh, I see. Got it.
This equation, GH is the same, and therefore this is a constant. That's how we started. But we compare that with 2 points. Remember?
Yes,
Okay.
I do.
All right, okay, so go back. So it's the same equation. And I just did that and then moved everything to the other side, okay? So same equation. And this is that. And now the velocity 1, because we assume that there's a streamline here and there's no friction. There's no friction here. And therefore, we end up with this equation here, this equation. Now, I would like to replace U2 with U1. So I go continuity, and therefore the velocity here, U2 is faster by the area ratio because we assume density is the same, incompressible. Substitute this one here. I end up with that equation. Very, very simple. Rearrange it a little bit and solve for the velocity. And if I want to have the mass flow rate, which is going to rho UA, substitute U1 here. This is the velocity. And then in this particular picture, I measure P1 minus P2 with rho GH. Sometimes we use the same fluid. So delta P and this rho are going to be the same. Okay, so that is the formula for the Venturi flow meter. And you actually translate that to the area ratios. Area ratios. This is we call it contraction. Mass flow rate based on the contraction and on the pressure signal you get here. It's a very simple device, works pretty well and fairly efficient. Now, people actually, this is a device that is being sold commercially, okay, for pipeline flow rate measurements. And it really depends if the flow becomes very, if the Venturi becomes very small, then there's going to be more friction. So there are corrections for the friction, let's see. And the manufacturer will give you a table like that. So this is a manufacturer data. And what we have here, okay, let me go through that. So first of all, it's the same equation we had before, but now we're adding CD. It's not the drag coefficient, it's called discharge coefficient or loss coefficient. And then it is listed here. This is a commercial data, by the way, it's a commercial manufacturer. And he shows the contraction ratio here. Okay, so what is the diameter ratio? If it's 0.8, then it's very large. And if the contraction ratio gets more and more narrow, then this number goes down, and then you have more losses. But this is versus the flow rate in the pipeline. So this is a very interesting result. In a moment, I get back to it. But the first observation is that look at the numbers here. We're talking about 2–3%. If you operate, this would be operational condition, maybe 2%. Okay. Then there's a number here, which is basically velocity, because the fluid has a fixed viscosity, has a fixed density, and this is the flow pipe, this is the pipeline diameter. So we already decided what are the diameter ratios of the pipe. So I bought this equipment, I installed it, and then I can figure out what is the loss coefficient based on this number. Anybody knows what this is? And this is my last question for today. Aerospace guys.
Is it the Reynolds number?
Reynolds number. Thank you very much. This is called the Reynolds number, which is density, velocity, some diameter divided by viscosity. Turns out that based on that, this is a universal speed. So now if I have oil flow or water flow, and then I keep this number here, for example, 10⁻⁶, keep the same thing, then I will have the same friction losses. Naturally, if viscosity is larger, then the table will move more to the left. I'm going to have more losses. Okay. Or if viscosity is larger, I will have to increase the diameter of the pipe in order to reduce the friction losses. Again, next chapter is going to be mostly about pipe flow, and we'll get back to that with more details. But this is a heads up that we do have this Reynolds number thing, which is very, very important. Okay, I think at this point, I would like to conclude the lecture. It was a pretty good, pretty good amount of material. Hopefully you digest it. Most of the things were mentioned are about the Bernoulli, flow measuring devices based on Bernoulli. And if there's any friction there, we try to not incorporate them, but if we want to use that, then we have to specify some friction loss coefficient or some loss coefficient, which hopefully are very, very small. All right. Thank you very much. And see you Thursday.
Professor,
Yes, sir. Question. Okay, let me just go ahead.
quick question. So number 2 on the homework says the cylindrical container shown above, and there's no image above. So is it referring to number 1 or?
You're talking about homework, which one?
The homework that's due this Thursday?
So what number is that?
Number 3.
Number 3. Stop share. Stop share.
Oh, I think I got it. Never mind. You have both pictures under number 1. I found